Hi everybody. This is going to be a video on section 9.3, which is on general results for first order linear differential systems. And in particular, we're going to begin our discussion with homogeneous vector differential equations. Okay? So I want you to recall, based on what we talked about in the last section, that a homogeneous vector differential equation has the form x prime of t is equal to a of t times x of t, where a of t is an n by n matrix function. Okay, so we have a nice theorem that deals with this, okay? So let me write down our theorem. The theorem is the set of all solutions to x prime of t is equal to a of t x of t is a vector space with dimension n. Okay? This is a big deal, okay? This is saying that they form a vector space with dimension n, which means, as we recall, that we can find a basis for it. In other words, we can find n things, n functions that span all possible solutions. Okay? So, how would we view this? Okay? Well, what you want to do, the reason why this is true is that you just want to view the following as a linear transformation. So first thing you can do is you can view it like this. So what I did was I instead rephrased it like this, and so I moved everything to one side and I get this, and this is the same as d minus a of t times x of t is equal to 0. What this means is that the solutions, the set of solutions, is precisely the kernel of d minus a of t. Okay? I mean, this is d is a linear transformation and a of t is a linear transformation. Both of these were shown in the last section, right? That these are linear transformations, or at least we stated it, right? And so that's exactly what the kernel is, right? It's the set of all x's that get mapped to 0 by this. And the kernel of d minus a of t is always a vector space. Okay. Now, why it has dimension n, that is a little bit deeper. We are not going to prove that, but it is important to know that it does have dimension n. And in fact, this guy is a subspace of Vn of I. Remember, we called Vn the set of all column n vectors, right? Column n vector functions. Okay, so let's keep going then. If x1 all the way to xn are n linearly independent solutions to x prime of t is equal to a of t times x of t, then any solution must have the form C1 x1 of t all the way to Cn xn of t. Okay, so once you find the n linearly independent function vectors, then any linear combination of them forms a solution, and so that is the general solution. Okay, so we have definitions for this. In the vector form, we have new terminology. So let's let x1 all the way to xn be n linearly independent solutions. Let me go ahead and call this guy star, because we're going to be referring to this homogeneous vector equation a lot. So let's let these be n linearly independent solutions to star. If you put them all in a set, we call that set a fundamental solution set. For star. Okay, fundamental solution set for star. It's actually also equal to a basis, right, for the solution space. But instead of calling it a basis for the solution space, we're just going to be calling it a fundamental solution set. Okay? Next, new definition. If we create a matrix using x1 to xn as columns, i.e., my notation is going to be x of t is going to be like that. These are all columns, okay? So I will put dots there to remind you guys that these are columns, okay? So what we're doing is we're taking that guy and we're creating an n by n matrix, okay? So if we do that, then we call x of t a fundamental matrix for star. Fundamental matrix for star. This is a really cool compact notation, right? We could take all n linearly independent solutions and stick them together into a matrix, and then that matrix encompasses all of the solutions, right? So note, if x of t is a fundamental matrix for star, we can write the general solution in a nicer, more compact way. So let me show you what I mean. If before we could write it this way, instead what we can do is we can write it this way. Okay, and what is C? C is just the column matrix that has all of our constants in it, right? Because if you look at what matrix multiplication is, x of t times c of t would be exactly what you get up there. So these two are equivalent, right? This is just more compact. Okay, but this and that mean the same thing. Okay, so this is just two ways of writing it. So let's go back and discuss this a little bit further. So we have a nice theorem. What's true about homogeneous systems? Homogeneous equations have a lot of nice things about them, just like homogeneous regular differential equations have nice things about them. So let's let A of t be a continuous n by n matrix function okay, if x1 to xn is a fundamental solution set for star. Remember, star is our homogeneous differential equation. Then the Wronskian of t is not equal to 0 for, let me just write it this way, for all t in I. Okay, so what we're saying is that if you have a fundamental solution set, then the Wronskian can never be 0. Okay, and so that leads us to what we call the Wronskian test. So this is going to be called the Wronskian test. So it's going to be called the Wronskian test for vectors Actually, let me write it this way. The Wronskian test for homogeneous vector differential equations. Okay, so first thing you're going to do, and by the way, let me just write out what we're solving here, right? Remember, homogeneous vector differential equations always look like this, okay? So there it is. Okay, step 1, first thing we're always going to do is we're going to find n solutions. x1 of t all the way to xn of t. Step 2, you're going to find the Wronskian of those guys. And you can plug in any point that you want. So let me just say at any convenient T naught. And step 3, if the Wronskian is equal to 0, then they are linearly dependent. And the better case, of course, is if the Wronskian is not 0, then they are linearly independent. Okay, this is what we want, right? Because if the Wronskian is not 0, then that means your n solutions are linearly independent, so they form a basis and they give you every solution. Okay, so let's do a quick example. We don't know how to find solutions yet, but in this problem, we're going to be given solutions and we just want to verify that they are linearly independent and all that good stuff. Okay, so let's consider the vector differential equation x prime of t is equal to ax of t, where a is equal to 1, negative 2, 2, 1, the matrix, right? And so there's our differential equation. Notice that A is a constant matrix, and I'm going to give you two vectors. Let's let x1 of t be e to the negative, sorry, 1 second here. Sorry, I wrote that wrong. It's negative e to the t cosine of 2t, and then e to the t sine of 2t, and then x2 of t is equal to e to the t sine of 2t and e to the t cosine of 2t. So part A, this is a two-parter, okay? I want us to verify that x1, x2 is a fundamental solution set for the vector differential equation, and use this to write the general solution. Okay, so that's the first part, and the second part, part B, is I want us to solve the initial value problem, which the only difference is that we're also going to add this condition. X of 0 is equal to 3, 2. Okay? All right, so let's start with part A. We want to verify that it's a fundamental solution set. So what we're going to do is we're going to check that each vector satisfies the differential equation. So let's start by taking the derivative. We're going to check each one at a time, okay? So first let's check x1. What's x1 prime? So if you take the derivative of the first guy, we need to use the product rule on that. It's going to be negative e to the t cosine 2t plus 2e to the t sine of 2t. And the bottom part derivative is e to the t sine of 2t plus 2e to the t cosine of 2t. So we want to know, is this equal to, remember it's a times x1, which is the same as a was 1, negative 2, 2, 1 times x1. x1 was negative e to the t cosine of 2t, e to the t sine of 2t, right? And let's just keep working with the right side to see if they are the same, okay? So how do you do matrix multiplication? Remember, you've got to do top row first. I need to do this times that column. And what do we get? We get negative e to the t cosine 2t plus 2 e to the t sine 2t. And then if I do the second part, it's negative 2 times negative e to the t is just 2 e to the t cosine of 2t plus e to the t sine of 2t. And we notice that these two are the same, right? This and this are the same. So x1 definitely solves it. Let's go ahead and check x2 now. So what is x2 prime of t equal to? Well, taking the derivative of x2 prime, we end up with e to the t, we're again using the product rule here, e to the t sine 2t plus 2 e to the t cosine 2t. And then the derivative of the second function was, or the second component, e to the t cosine of 2t minus 2 e to the t sine of 2t. So is that equal to a times x2? Well, this is, again, the matrix 1, negative 2, 2, 1, and this time we're going to put in x2, right? And x2 was e to the t sine 2t, and then e to the t cosine 2t. And this is equal to, again, do matrix multiplication on this. You get e to the t sine of 2t plus 2 e to the t cosine of 2t. And the bottom one's going to be negative 2 e to the t sine of 2t plus e to the t cosine of 2t. And we notice that this and this are the same thing, right? They're exactly the same thing. Okay. So we have now checked, so what does this mean? This means that x1 of t and x2 of t are both solutions. But we're not done, right? Why are we not done? Because when it asks us to show that it's a fundamental solution set, right, it means we also need to show that they're linearly independent. Okay? So are they linearly independent? Let's see. We need to use the only way we know how, right? Use the Wronskian. So what is the Wronskian of x1, x2? It's going to be the determinant of, all we do is put the solutions as columns in our matrix, okay? So it's going to be this is our x1, and then this is our x2, and then we're taking the determinant of that. So this is equal to, the determinant's going to be, we just do a determinant of a 2 by 2 matrix. So when you multiply these together, you get negative e to the 2t cosine squared of 2t minus e to the 2t sine squared of 2t, which is actually, if you factor out the negative e to the 2t, the rest is just 1, so it's just negative e to the 2t. So is that equal to 0 everywhere? Of course not. So this is equal, so if we plug in, remember we can plug in, let me actually do this in 2 steps, okay? So this is the Wronskian in general. So what would the Wronskian, if we plug in, we can plug in anything we want. So if we plug in 0, what do we get? We get -1, which is definitely not 0, right? We're allowed to plug in any convenient point we want. So what does this mean? This means that x1 and x2 is indeed a fundamental solution set. Okay, so we're done with part A, right? Actually, we're not quite done. This means that we need to write the general solution. Sorry, I forgot it asked us to do that. So this means that x is equal to, we're going to write the general solution like this, right? It's going to be c1 times x1 of t plus c2 times x2 of t. This is how we would write the general solution, or if we want to write it with the actual, functions written, we can. It looks like this. Oh, sorry, that was the derivative. I wrote the wrong thing down. It would be like this. Plus c2 times e to the t sine of 2t, e to the t cosine of 2t, right? This would be the general solution. Okay. Now there is, and I want to just show you guys that you can also write this in matrix form. So the way you would write it is like this, right? So you'll notice I'm writing it as let me erase this really quick. Okay, so this is how we would write it, okay? This is the same as before we wrote x of t is equal to capital X of t times vector c, right? This is just a way that you can write it using matrices, okay? Both the same thing, okay? These are both the general solution. All right, two different ways of writing it. Now, I want to jump to part B because part B asks us to solve the IVP, right? Remember the initial value problem? So for part B, remember we're given that x prime is equal to ax, but we also know that x of 0 is equal to the column vector 3, 2. So this means that 3, 2, which is x of 0, I could set that equal to what happens when I actually plug 0 in to our general solution, right? So when you plug 0 in, remember it was negative e to the t cosine of 2t, but e to the 0 is 1, cosine of 0 is 1, so you just end up with -1, and the bottom gives you 0. Oh, let me back up here. I forgot the constant. It's c1 times, you get -1, 0. And if you do the same thing on the other guy and you plug in 0, you actually end up with 0, 1. Okay? So this actually leads us to a system of equations, right? It's a very simple system of equation, though, because of the zeros. This means that negative c1 has to be 3, and also that c2 equals 2, but this means that c1 is equal to -3, right? And so we end up with x is equal to -3x1 plus 2x2. This is the concrete solution to the initial value problem, which is the same as negative 3 times, remember, these are functions, right? Okay, we get this, right? This would be our solution to the initial value problem. Now, understand, guys, that this can be written in component form. If you wanted to write it as two different components, you could do that, right? You could write it this way. It wouldn't be vectors anymore, sorry. So you can write it like this. x1 of t is equal to 3e to the t cosine 2t plus 2e to the t sine of 2t, and x2 of t is equal to negative 3e to the t sine 2t plus 2e to the t cosine of 2t. Okay, so this would be in component form, but of course, we like vector form. It's a little more compact, and so this would be vector form. And of course, as a third form, we've also got matrix form, if you want to use the fundamental matrix to do your problem. Okay? All right, so all of that was for homogeneous, right? Now, what about the non-homogeneous ones? These are very complicated, so what I just want to do is write down a general result here, and this will seem familiar to you, okay? So how about non-homogeneous vector differential equations? Remember, a non-homogeneous vector differential equation looks like this, right? What is the form of these? They look like this. X prime of t is equal to a of t, x of t, but then there's also a b vector function, right? This is the special part. This is what makes it non-homogeneous, right? You've got a b of t there. And so to deal with this, I'm going to call this star star, since we've been calling star the homogeneous case, right? So let's go ahead and write down the theorem. And this theorem is going to be very familiar to you because it's going to be just like chapter 8. So let's let a of t be a matrix function. And let's suppose that it's continuous on some interval I. And let's let x1 to xn be a fundamental solution set to the, now we haven't named this yet, but let me call it the associated homogeneous equation. Remember this? Okay, so yes, we look at the associated homogeneous equation, where you just essentially pretend the b of t is not there, and let's suppose that x1 to xn are all of the solutions, okay? Then, if xp of t is any particular solution to star star, so let's suppose that we have any particular solution to star star, then every solution to star star is x of t is going to equal c1 x1 of t plus all the way to cn xn of t plus xp of t. Okay? This should be familiar to you, right? And what did we call this before? We called this xc of t. And so we end up with having the exact same form as before. What we're saying is that the solution x of t is equal to, let me make this more clear. All of this is just xc of t, okay? Remember we called that the complementary function. So it's like the complementary vector function. So what we're saying is that you solve the homogeneous vector differential equation, and that gives you the complementary vector solution there. And that's what we have, our xc. And then any particular solution to the non-homogeneous just gets added to that, and that becomes your general solution. So this is the general solution to star star. Right? So this should feel familiar to you, right? This is exactly an analog to chapter 8 when we first learned in the first few sections of there. Actually, I believe it was in the first section. We learned in 8.1 or 8.2, one of those, we learned that the solution to the non-homogeneous differential equation is just going to be the complementary function plus any particular solution. Okay, guys, we're going to stop here. However, in the very next section, we're going to learn how to solve these for special types of coefficient matrices, okay? Thanks very much for watching.